Whoa! Statistics rules! I've got a rolly chair. I can finally teach in a rolly chair again. Man, the glory. The glory is back. Ready to go. All right, guys. It's game time. I don't know about y'all, but I think it's time for us to get some learning done. You guys have had enough. Your brains are nice and rested, ripe for molding. All right, let's go ahead and get started. So we just did confidence intervals. If you didn't get a chance to watch the recap of before, that video is available on the website. Go check it out. We're back in the courtroom now. We've done a confidence interval for a difference in two proportions, and now we're going to talk about significance testing or hypothesis testing, a difference in two proportions. Interesting, okay? So we're back in the courtroom. I think it only makes sense for us to watch the entire first season of Cop Rock via my YouTube channel. No, sorry, I meant let's go ahead and review what we did with a regular proportions significance test while we're on here. I got to make sure I got my I have my. Oh, there we go. Oh, let me get my ink ready. So first thing we do is, the process is essentially the same as what we did before, except we're testing something a little bit different this time. Okay, so let's take a look at what we did. So remember the test we did in class was with the Safeway Monopoly tickets. Shalansky had said, hey, the claim, she found a source that said the claim is that 29% of the tickets have a free something in them for us to use or a discount. So we kind of tallied those, and everything else we considered kind of a failure. Successes were the things that had the free ticket. So P represent, so we state the proportion that we are estimating, the parameter that we're estimating, or the parameter that we're discussing. We have we take basically when we're entering the courtroom of logic and statistics, we take the claim as fact and we say, okay, if your claim is true, then when we conduct a sample, it should probably somewhat support your claim, or if it doesn't, maybe it supports this alternative hypothesis. So in the state portion, we say the parameter of interest, we say our hypotheses, and we say the significance level at which we will be testing. In the plan stage, again, we're going to say, and this is going to be slightly different because we're looking at a different parameter, but basically the same. In the plan stage, we say the Z interval. That's supposed to say Z test. Hilarious. Okay, so we want to perform, we'll be doing a two-sample Z test here. The conditions are slightly different. We'll go over those in just a minute. But basically the same as we did with the interval. They are exactly the same as we did with the interval. And then there's a change that we have to make up here. So we checked our conditions. We stated the test that we were going to use. And the do phase is we calculate p hat. And we calculate this thing called a standardized test statistic. And basically what this standardized test statistic does is it tells us when we go out and we collect a sample, it says, okay, assuming your claim is true, assuming that the proportion is actually 29% of, good rewards, then how rare would our sample be, assuming that that's true? So it give us the number of standard deviations, or rather, that we expect it to fall from that mean. Okay, so the way that we do that is we put in our sample, it gets popped down into here, and then this is our hypothesize, our null value, our p naught, which is 0.29, and then down here our standard error, or standard deviation of our statistic rather, is based off of our hypothesized p-value. So we're assuming this is true. So assuming that this is how things are spread, assuming this is how things are centered, there's our spread, there's our center, how rare is this sample value? And so that's what this p-value is. is we say, well, we got a p-value of 0.59. What does that mean? That means that we can expect to, basically assuming that this is true, we can expect to get a p hat, or a sample statistic of 0.306 or less, right? Coming from our alternative hypothesis, we can expect to get that or less roughly 60% of the time. So how rare, or how rare was our sample? You know, it wasn't super rare. It's something that probably happens pretty common. And so we come to the conclusion that, hey, since our p-value, since we did, and you can do, normal CDF to get this area, to get your p-value, since our p-value is greater than the alpha that we set at the beginning of our test, we don't have convincing evidence to say that the proportion is so we fail to reject H naught, right? We don't have convincing evidence to say that it's less than, and we could potentially say that in the future, but that's why we say fail to reject. So we don't have convincing evidence that the proportion of successful tickets is less than 0.29. That's the whole process. It's just like a court case. Okay, so how is testing a difference in proportions? How is this process any different? Let's go ahead and keep cruising here. So what is new? The first thing that is new is that H naught is going to look like a difference. So H naught, again, we're using our parameters here. H naught is going to be P1 minus P2 equals some value A. Most of the time, we will be using A equals 0, because if A is equal to 0, notice you have P1 minus P2 would be equal to 0. So the null hypothesis is that the proportion from one population is equal, we could add P2 to both sides, is equal to the proportion of the other population. You should never write your null hypothesis like this. I mean, you can write it like this. Don't write it like that. But that's what's changing. So we typically are going to write 0. The null hypothesis is that these two proportions are the same, and we're trying to prove otherwise. And that's usually what it ends up being. Okay, what are our alternative hypotheses? Well, they're exactly hypotheses. They're exactly like what you would think. You'd say P1 minus P2 is not equal to that value A, or not equal to 0. P1, that would be, this is a two-tailed. Don't mind the baby noises happening in the back. So this is a two-tailed test, and these are both one-tailed tests. Okay, and then you can test whether it's bigger than A or whether it's less than A, but you have to decide. And choosing these through alternatives, I mean, it shouldn't be any different than what we've done before. We'll usually use A as 0. Okay. All right, so there's a problem here. Notice back when we did this, our standardized test statistic, we used this as our, from our sample. This came from our sample. This came from our hypothesized value. And this came from our hypothesized value. What we are assuming the null hypothesis is true. Just like when Dylan came and said, I'm an 80% shooter, right? We're assuming that's true. And then we say, well, Dylan, if you're an actually 80% shooter, then what's the chance that you actually did as bad as you did shooting baskets just by random chance, right? And it wasn't very good, right? That's kind of our p-value. But our null hypothesis, well, that's a problem because typically we use for the standard deviation, we would normally use this ginormous formula. But this formula involves p hat, and we don't have a p naught, right? We don't have, for our test, if we go back, we don't have, if this is our null hypothesis right here, we don't have a p naught. We're just saying there's no value. We're just saying, well, they're equal. Well, we don't know what P1 and P2 are, so we can't use this. We can't use that. I know, he's really upset about it. I'm telling you. He's just, we're out of, Oscar, we're out of options, buddy. Totally out of options. So instead what we do, and this is kind of weird, but we're saying like, hey, since we don't have a value to use that represents the population, we're going to do the best thing that we can, and we're not going to use these samples separately. We're going to do what's called pooling. So this is our p-hat right here. This is a new p-hat, but what we use for our test statistic is, I know you guys are going to kill me, so we have this, what's called a pooled p-hat. I'm going to call it pooled p, if you guys don't mind. Pooled p-hat, which is you take the number of successes in both samples combined, and you divide by the number of individuals in both samples combined. So it's basically the total number of successes in either population divided by the total number of both sample sizes. So this would be N1 plus N2. This is the number of successes in each. And hopefully this will make a little bit more sense once we see an example here. So yeah, normally our standardized test statistic here, what is it? Oh, I forgot to clear this one out. That's okay. Normally our standardized test statistic looked like p-hat minus the parameter divided by the standard deviation of that statistic. So let's take a look here. Well, our statistic, the thing that we are calculating is p-hat 1 minus p-hat 2. What's the parameter that we're estimating? Well, that's p1 minus p2. But our null hypothesis is usually that these two things are the same, that p1 minus p2 is 0. So most of the time, right here, we are just going to use the value 0 in place of this. So you're just going to see me sub in 0 because that's what we hypothesized, right? p1 minus p2 is 0. Okay, cool. And then down here, we're using this p-hat thing, which is this pooled. So we do this the same formula, except we have N1 and N2, and we have this new pooled p-hat, okay? That's kind of in quotes. It's kind of like slang. Yo, this thing is pooled. Anyways, that's the equation that we're going to use to do our test. Enough jibber jabber. Let's do our test. We're all learning about pandemics and epidemiology and the spread of disease, so I figure we may as well talk about COVID-19 for our example. I've been checking the Worldometer website for updates, and I was looking at, I'm going to go ahead and fit this here. I was looking at this data for the fatality rates in different countries, and I wanted to talk about the United States, but I think that we're not at the stage we are in the infection. I don't think the United States is a good one to compare to other countries because we're so new based on current data. So I thought what made more sense was to compare two countries that are kind of close to each other, that started the infection roughly at the same time, and trying to compare the spread of the disease. And then this data was from this morning, and it's already out of date, but that's fine. What's today? I need a date. What's the date?
What?
What's the date? The
24th.
24th. Thank you. Someone's keeping track of time. So yeah, this is the morning of the 24th is when I pulled this data. That is March 24th anyways. So I think the two countries that, so we're asking a question. So what is this hypothesis test or significance test for just difference in proportions answers this question. Is the fatality rate different in different countries? So is the fatality rate different in different countries? That's the kind of question that we can answer with a significance test with a difference in proportions. So we can assume, so coming into the court case, we assume that the fatality rate in two countries are the same, and then we're going to say, wait, so if the fatality rate is the same, what's the likelihood that we're getting the results that we get? Sweet. So let's go back. I think in looking at this list is just the top. Which one makes the most sense for us to look at? I'm thinking it is France and Spain. They're right next to each other. They're at a similar stage in the infection, and we can. Their numbers look somewhat similar, so let's take a look. Now, the math for this is going to be a lot because the numbers are so big. We have to do a little fudging, but that's okay. All right, splendid. So let's fit this to the screen. So the countries that I chose were Spain and France. And so I made a little two-way table here, excuse me. And you'll notice that if you look at any country, the total number of cases, I'm not looking at cases that are not, I'm only looking at cases that are closed. So I'm only concerned with non-active cases. So ones where people are actually, where people have perished or people have recovered, not active cases. And so I know that Spain and France are currently still in kind of the throes of the virus, but they seem to have a similar number of people recovered, even though total cases is somewhat close, but not. Anyways, they look like the correct countries to compare. So I made a little table here and I said, of the cases that are closed, that means ended in somebody dying or someone recovering, 2,800 people have died in Spain and 3,794 have recovered, meaning for how many cases that are being closed, although this is not on the table, we can do this pretty quickly. There are 6,594 that have come to a conclusion. In France, you have 1,100 people that have perished, 3,281 that have recovered, for a total of 4,381 total concluded cases in the country. So the numbers are similar. This is an absolutely devastating virus. But what looks like for a number of people that have perished total in those two countries, 2,900. Number of people that have recovered, 7,075. Okay, so we have our data here. Let's go ahead and we're going to run through a hypothesis test for this. Okay, so state. Let me pull up my notes so I don't screw anything up here. Thank you for your patience, everyone. All right, let's get her going. Let's get her going. So, for us to do our test, the first thing we do is we are going to state the hypotheses that we're going to use. So I'm going to say we plan to test. Let's see here. Now, H naught is going to be that our null hypothesis is that the fatality rate in each country is the same. And I'm going to say PS for the proportion in Spain minus PF, which is the proportion in France, should be 0. So the null hypothesis is that they have the same fatality rate, and our alternative hypothesis. Now, before we looked at the data, people are talking about this virus has a fatality rate. Well, does government or does the country you're in really make a difference? The way that disaster relief is handled is kind of changes at the border. So this will be an interesting experiment, or interesting test, rather. So the alternative hypothesis, I think what makes sense for me, if we were to not look at the data, we want to say, are these countries we would have no reason to believe one country would be doing better than the other. So I think the test that makes sense is that PS minus PF is not equal to 0. So we're doing the two-tailed test. We're saying the difference, they're not equal to each other. The alternative hypothesis would be they are indeed different, the fatality rate in those two countries. So let's next thing we have to do. So we've stated our hypotheses. Now we have to define what these things are. So I'll say where, there's our hypotheses, where PS is the true proportion of fatalities in Spain from concluded cases of COVID-19. Bingo. Okay, so that's what PS represents. and PF is the exact same thing, except, and rather than write it, I'm just gonna, you know what, I'm gonna cheat. Rather than write it, I'm gonna go like this. Yoink. Copy, paste, deal with that. I know you guys can't do that in your notes. Sorry, don't feel bad for you. And then I'm gonna come through and erased Spain. Wow, I am a cheater. Cheater, pumpkin eater. And make sure I reselect my ink. Probably could have been done by now. Please don't be mad at me. I just made, yeah, okay. And PF is the true proportion of fatalities in France from the concluded cases of COVID-19. There, okay. Interesting. The last thing that we have to state before we begin, I'm going to state our significance level. We will test using alpha equals 0.01. I want us to be very, very sure. We could use something even less if we so choose, but I want us to be very, very sure that there is a difference for us to come to that conclusion when we're done. Okay, so we have stated our hypotheses. We've stated the parameter of interest, which is this difference here, and we've stated what these are. And now we're working with our significance level. So let's go on to the next step. Remember, we're doing speedy here. State, plan, do, interpret, or conclude. And to plan, what do we have to do to plan? We need to state the test that we are using. I'm going to switch colors if you guys don't mind. Is that okay? Let's switch it up. We're going to switch it up. Red? No. Blue? Yes. Okay, plan. What's our plan? We plan to do a 2-sample. We're going to sample 2 countries. 2-sample z-test for a difference of proportions, which is P1 minus P2. Bingo. So that's the plan. Oh, hey, Buster. You going to give me the duct tape? Thank you. Okay. Before we move forward with our test, Oscar, what do we have to check for? Randomness, independence, and the large counts condition. Oscar, you're so good. He's already got his stats down. See, if he can do it, guys, you're not going to have a problem at all. Randomness is the first one. We're going to have to fudge these a little bit here, folks. I'd rather do something relevant, but I'm going to make the argument that the disease is spreading randomly. How can I make that assumption? I can make that assumption because you're kind of contagious before you even are showing symptoms. So I'm going to assume that it's the disease is spreading randomly in each country. I know, it's a sad deal. It's a really sad deal. Okay, 10% condition, or the check for independence. Now this one's a little rocky, because if we go back, let's take a look at that. The total number of cases, 6,594 for Spain is actually bigger than 10% of the total number of cases. I would imagine, based on how many new cases are popping up each day, that they're going to get to 65,000. They're going to get to a number of cases that is fairly large. And so I think that how we're going to argue this basically is that 6,594 is likely less than 10% of all concluded cases. Concluded cases Spain will see. Okay, so the population is still growing effectively. People are still becoming infected. And so I think based on what's projected, I think they're going to end up seeing more than 60,000 cases. And similarly, $4,381 is likely less than 10% of all cases France will see. I see Spain, I see France. Let's see, of all cases France. Brutal. That's pretty brutal. That's a lot of cases. And then the last one is large counts. Okay. Now, to do the large counts condition, you're checking N1 times P hat 1 and making sure it's bigger than or equal to 10. Well, I know that the total number of cases is 6,594. I'm using ones. Ha ha ha. P1, this is supposed to be PS and PF. There. Fix that again. Aha. Okay, so this is PS and PS, or NS and PS. So basically, the total number, our sample size in Spain times the probability of perishing from the disease. Well, we know that we're determining this from the number of fatalities that have happened, and we already know that. And we know the number of fatalities is 2,800 in Spain. So this times the probability of death is going to give us this number anyways, and we know that that is greater than or equal to 10, so the large counts condition is satisfied. I feel guilty talking about this so casually. 1 minus P hat S is, so NS, the sample size from Spain, minus the probability, 1 minus the probability, that gives us 3,794 people that have survived and recovered, which is great news. That is also greater than 10, so we're good. And the last one is N sub F and times P hat for F. And that is equal to 1,100. If you look at that table, which is greater than 10, and NF times 1 minus P hat F is equal to 3,281, which is also greater than 10. So good. Basically, when you're doing tests for proportions, you have to see at least 10 successes and 10 failures. You have to see that, which is how we determined the number of Monopoly tickets we needed. I said, hey, if there's a 30% chance that we get a success, and that's the limiting factor here, successes, we need to make sure we get at least 10 successes. We did some math there to figure out roughly how many tickets we would need. Okay. So we have 10 successes, we have 10 failures. Our large count condition is satisfied. I had to do a little fudging on these two, but I think we can argue it that it's fair. Let's move ahead. Do. Now we got to do the math. Do the do. Okay, couple things we have to calculate. First thing we have to do, I'm going to do P hat for Spain. The probability of the probability or the fatality rate for Spain is equal to 2,800 divided by 6,594, which is 0.425. And the fatality rate for France is 1,100 divided by the total from the sample, which is 4,381. And the fatality rate there is roughly 25.1%. Okay, so that's great. So we calculate, it's not great, that we calculate the fatality rate for each country, and then now we are going to calculate the pooled P hat Pooled p-hat, remember, is what allows us to assume this is kind of the best we can do for assuming that the null hypothesis is true, and this is going to be 0. So we're getting to that test statistic in just a minute. Z. So to calculate the pooled value, we do the total number of fatalities, it's just 2,800 plus 1,100 divided by the total sample size between both samples, which is 6,594 plus 4,381, which is 3,900. That makes sense. Divided by the total, which is 10,975. So we get a pooled p-hat of 0.355. And that's what we're going to use. And we'll use these two as well, but we use these two in the numerator, and we'll use this in the denominator for our standardized test statistic. So I'm going to go ahead and switch colors for that. We're going to go ahead and use purple here. Coming down, so let's calculate our standardized test statistic Z. That is going to be equal to our sample statistic, and that's probably going to have to be a smidge bigger, which is p-hat S minus p-hat F, okay, minus PS minus the difference between these two all over this big thing. You know what? I'm just going to, if you guys don't mind, well, we're already there. Let's just keep going. Over p-hat, which is our pooled p-hat, and 1 minus pooled p-hat over n1 plus pooled p-hat times 1 minus pooled p-hat over n2. Okay, let's go ahead and plug stuff in. This ends up being 0.425 minus 0.251. And by the way, guys, you could have switched the order of these. It wouldn't really matter. The difference that we're a hypothesized difference, we're assuming the null hypothesis is true, is 0, so that goes away. And then in the denominator, we have the square root of our pooled p-hat value, which is 0.355 times 0.645 all over sample size 1, which is 6,594 plus 0.355 times 0.645. Again, that's the 1 minus value over 4,381. And so you can go ahead and do lots of math here. And when you do lots of math, you end up doing this minus that minus 0 is really just this minus that, which is 0.174 divided by, I'll let you do the math here and check my math, but this is going to end up being 0.009327. And when you divide these, we get a test statistic of, drumroll please, roughly 18.6. So how rare would it be? How do we interpret this value? Basically, we interpret it this way. How rare is it, assuming that these two countries have the same value and we have sample sizes of 6,594 and 4,381, how rare would it be to get a difference that is this big? And you're probably thinking the difference is very large, and it's so rare, you're about to see. Okay, so here's, let's say this is the curve. You will get a difference this large based on these sample sizes. You have to go out 18 standard deviations in either direction out here. You will get something like this, a difference this big or more extreme, seldomly, never, okay? And so next we have to find our p-value. And to find that p-value, I'll do this in green. Our p-value is equal to, whoops. Our p-value is equal to, let's go a little bit further. And let's just go ahead and I'm going to scroll all the way down like this so we can write at a decent size. Beautiful. P-value is equal to 2 times, right? Because you could, you have both sides. So you have to calculate the area under the curve to the right and to the left. And we're talking about going out 18.6 standard deviations on the standard normal curve or further in either direction. So 2 times the probability that z is something that's symmetric, right? That z is greater than 18.6. We know the answer is going to be less than our significance level already, so which is equal to 2 times, and then we'll use normal CDF. Almost done, guys. Hang in there. Lower equal to 18.6, or you could do the other side, it doesn't matter, comma, upper, I'll use equals 1,000, mean equals 0, and standard deviation is equal to 1. Okay? So you do that math, you end up getting a number in scientific notation because it's so small. You get 1.72, roughly. Yours might be a little bit different. Mine is, I'm going to double check because I used actually different numbers for the first time I did this. Slightly different. I rounded differently. So I'll do normal CDF 18.6. Oh no, that's roughly correct. To 1,000, yeah, 1.72. So 1.72 times 10 to the negative 77th. So it's effectively 0. Multiplying by 2 is not really going to do a whole lot. Our p-value is 3.44 times 10 to the negative 77th. Yeah, which is approximately 0. So what does this mean? What does our p-value mean? Again, that is assuming the null hypothesis is true. That is assuming that the fatality rate in each country is the same. We could expect to see a difference this large almost never. Okay, like 0% of the time. I mean, there is a percent and there is a possibility, but it's so negligible that it's not even worth mentioning. So what do we conclude? What's our conclusion? How do we interpret these results? This is how we get started. Whoops. We say because our p-value of 3.44 times 10 to the negative 77th is less than alpha, which is equal to 0.01. We reject H naught. We reject the idea that these two countries have the same fatality rate. So you can't say what caused that, but I mean, if we're actually talking loosely, it's likely the way, something that has to do with the countries themselves, so the way that they're being governed, the way that the disaster was handled, so on and so forth. We have very strong evidence very strong and convincing evidence that Spain's fatality rate from COVID-19. What am I, 6? God, look at that. Okay. Cases is different than that of France. Okay. And I think since our alternative hypothesis was different, we have to state different. But let's be honest, folks. I think based on this, we can conclude that because it's so convincing and it was so one-sided, we can conclude that Spain's fatality rate is larger than France's. Okay? So how do you do this and check this on your calculator? You can do this thing called a 2-prop z-test if you go to your test options, and basically you would enter in, now these are not, this is just out of the book, so these are not the numbers that you have, but you enter in the number of fatalities from the total number of closed cases in Spain, and then the number of fatalities and the total number of closed cases in France, and you will type this in, and you can draw a picture of what the curve looks like. And you will also get the test statistic. It'll give you your p-value. It'll give you your pooled statistic, and so you can check all your math here. And so this is a huge advantage for you. And I can almost, I mean, it's very likely you'll see something like this on the AP exam, although there have been some key updates, and I'll go over, once we know a little bit more about that AP test, I'll go over, make a video about the updates that are happening. How would this change if it were a one-tailed test? Well, if we go back to our calculations, the only thing that is going to change is that you wouldn't multiply by 2 right here. That's it. And if you didn't multiply by 2, it's just making your test pretty much more convincing. So, and it'll change your conclusion slightly. You can say directly in your conclusion that, you know, it's likely larger. The proportion in France is larger. Okay, that's it. That's all I've got for you today, guys. That was just like, I don't know, like 18 hours of statistics. Thanks for watching. Thanks for tuning in. I hope this was helpful, and I'd be happy to answer questions about this in our Q&A session, and hopefully we have a schedule developed. I'm shooting this before we have a schedule developed. So check in on Google Classroom if you have something you'd like me to reteach or you have any questions or concerns. Thank you very much, and I hope you guys are doing all right.